So today we'll zoom out of the atom and we're going to look at diode characteristics. And then from here on in the later chapter, we'll look at circuits made with diodes. Now, as CPE majors, you'll be mostly working with the data and signal end of these devices. So as I was saying, as CPE majors will be working with the data and signal end of these devices. So we are not, we'll still behooves every student to understand how these devices work and how they can be analyzed, right? We're not going to do heavy duty or very in-depth circuit analysis, but we look at a few models that can be used for diodes and transistors and FETs and MOSFETs. Now, these are nonlinear devices. These are, unlike the resistors, capacitors, and inductors, these are complicated devices. So there's no one single model that can describe the operation of these devices. So depending on what kind of application and what kind of system we have, we would choose different models for every application for our needs. So there are very simple models that we can use to perform a very quick analysis. And especially like, let's say we are doing the lab 1, lab 2, we can use these kind of models to perform a quick analysis, determine whether the diode is on or off based on the input conditions, right? So let's first take a look at the characteristics. So this one here, this one here. So this shows you the diode VI characteristic and the different types of diodes that we'll encounter. So in the diode VI characteristic, this region in the first quadrant is known as the forward bias. This here in the third quadrant is known as the reverse bias. So what does forward bias actually mean? Well, forward bias means diode VD is positive or greater than 0. And more importantly, forward bias in simple terms means that the anode voltage is at a higher potential than the cathode. And the difference between the potential, meaning VD, must be greater than VBI. That is the built-in junction potential. So the voltage that we are applying to the diode, first thing, must hold the anode at a higher potential versus the cathode. And secondly, the voltage must be enough, the diode voltage must be sufficient to overcome the built-in junction potential. Okay. For all other cases, the diode is essentially off and it's not conducting. Okay. So if we take a look at this section of the forward bias right here, we can see voltage is positive, meaning the anode is at a higher potential than the cathode, but the current conduction is 0. As we increase the voltage, like 0.1, 0.2, 0.3, 0.4, you see a small amount of current starting to flow through. Sometimes it's even so small that we cannot measure it by conventional means. And then as it starts approaching VBI, we see an exponential curve right there. Not exponential, but upwards curve. So the voltage is increasing, the current is also increasing at the same time, and it takes a sharp turn upwards where the junction is overcome. Diode voltage is now larger than VBI, and then a large amount of carriers cross the junction, so that results in a heavy flow of current through the diode. The change in the voltage is very small, but the change in the current is correspondingly large. Hence, nonlinear. Okay, nonlinear. So again, forward bias, first condition is the anode must be at a higher potential with reference to the cathode. And then the second one is that the voltage that is being applied, VD, must overcome the junction, built-in junction voltage, built-in junction potential. So when the diode starts conducting current, we represent VD as positive, ID also as positive. VD positive means diode voltage VD is measured at the anode. So I would write VAK, measured at the anode with my reference at the cathode. So anode is connected to the positive terminal of the meter, cathode is connected to the negative terminal of the meter. When someone references diode voltage, we are always referring to the voltage at the anode. And the reference point is at the cathode. Positive at the anode, negative at the cathode. ID similarly would be flowing. ID would be flowing according to that polarity convention. Now, when the voltage turns negative, meaning we are moving in this direction towards the left, third quadrant, it crosses the origin. Diode characteristics always pass through the origin. Okay. So if you're not applying any voltage, or if the voltage at the anode and the cathode is exactly the same level, then the diode is off. Okay. In the forward bias, when the diode is conducting current, we say the diode is on. In reverse bias, voltage at the cathode is higher than the voltage at the anode. So VD is less than 0, less than or equal to 0. In real life diodes, we are not using an ideal diode model. So real life diodes require about 0.6 to 0.7 volts to turn on for silicon. So if it's less than 0.6 volts, 0.5, 0.4, 0.3, then the diode is going to be off. It's not going to be on. If the single most criteria for diode to turn on is right here. If this criteria is not met, then the diode is off. The quick way to look at it is, if the cathode is at a higher potential than the anode, diode is off. If both voltages, both terminals are at the same voltage level, meaning 5 volts and 5 volts at both anode and cathode, the difference between the terminals, VD, is equal to 0, diode is off. As the voltage turns negative, meaning the voltage of the cathode keeps rising, we are applying a negative voltage. So minus V results in minus I. When you reverse bias the diode, recall from last lecture, we are applying positive of the supply voltage to the N-type material, negative to the P-type material. That attracts the minority carriers. The minority carriers in each semiconductor type are now free to cross over the junction. So in reverse bias, the minority carriers are moving with the field, so they're free to cross the junction. So a small amount of current is flowing through a diode in reverse bias in the opposite direction. Now, this current is known as the saturation current because it quickly saturates at a certain level. That level depends on the geometry of the device as well as the doping profile of the semiconductor. Okay. Typically, the saturation current is in the order of like nanoamps and picoamps, so small that we can't even like measure it, and remains pretty constant. If you try to measure this in the lab, all you will see is 0. You won't see anything else. All right. So now in the reverse bias, diode is off. The only thing that is flowing is the saturation current, IS. And saturation current, IS, is a function of the geometry and the doping profile. Hence, it is up to the designer and the manufacturer. So this is always specified in the data sheet, manufacturer's data sheet. So not picofarads, picoamps and nanoamps. It's part of the manufacturer's spec sheet. You can find it value in the data sheet. So that's saturation current IS. Now, If you keep on increasing this voltage, you go from 0, -1, -2, -10, -15, 20, 30, 40, 50. The diodes, you would ask, why would we operate the diode in reverse bias? Well, there's intentional, and sometimes it will also be unintentional. Intentional are of two kinds. Use a circuit, you have a AC signal that goes both positive and negative, like we use for the peak detector and the voltage multipliers, where the diode, if you apply a sine wave or a square wave or any kind of AC signal that has a positive value and a negative value, the diode is forward bias for one of the cycles, and it will be reverse bias for the other cycle, depending on your connection, right? If you take a straightforward connection where you're applying a sine wave or a square wave to a diode with positive at the anode, then the diode would be forward bias in the positive half cycle and would be reverse bias in the negative half cycle. So in the reverse bias, the diode must be able to withstand whatever voltage we're applying. Okay. Does that make sense to everyone? Right. So based on our application, a diode would be intentionally in reverse bias. Yes. Dan, you want to have a question? Okay. So that's one of the cases. Experiments with diodes in reverse bias. The other thing that happens is it must withstand it without the junction breaking down. So what does breakdown mean? Breakdown is something that occurs in reverse bias when the voltage that is applied in reverse bias to the diode exceeds a certain level. Say junctions. While the current through the diode increases exponentially. You see a slope in this characteristic right here, where it's marked number 2. This slope is very exaggerated. This slope is actually very steep. It's near vertical. Okay, it's a near vertical slope in the reverse bias. So it's one of the properties of a semiconductor diode that once the junction breaks down, there's a flood of charge carriers, level saturates. Current can keep on increasing while the voltage across the diode is held nearly constant. And this property is actually used and implemented in something known as a Zener diode. Okay, these diodes are specifically manufactured to operate in the reverse bias because it can handle large amounts of current while holding the voltage across itself constant. The diode will remain constant, meaning the input voltage can keep on increasing, but the diode voltage remains the same. So energy and power properties, power laws, and energy laws will all apply. The only way the voltage can remain constant is if the current through the diode increases, which is where this characteristic is very useful. In the reverse bias, we talked about breakdown, and I mentioned Zener, right? So breakdown occurs due to 2 different kinds of mechanisms. Electrons and holes to be generated. So in the reverse bias, but typically we would have very low values of minority carriers. Now we might have a higher number of charge carriers that are present. And so they're quickly able to break down the junction. It does not require a high electric field. These Zener breakdowns can occur at very low voltages. Typically, Zener breakdowns occur in 5.6 volts or less. Okay, something less than 5.6 volts. An avalanche breakdown occurs in, that was electric with voltages applied in excess of 5.6 volts. But in general, it has become convention to refer all reverse operation as Zener diodes. So if you have a Zener diode, it could be working in Zener mode or it could be in avalanche mode. But in general, convention just states that everything is Zener. Okay, so everything is a Zener diode, Zener. Even though the effect might not be due to Zener effect, it could be avalanche effect, but it is referred to as Zener diodes. Avalanche occurs due to a very high electric field that is applied. Now, typical diodes that we operate, let's see, the 1N4000 series. Have you all used that diode before? 1N4000? It's like a black encapsulated cylinder with like a gray silver band at one end. You'll use it in 215, I mean 245 perhaps. Okay. No, not the Schottky ones. So this is, these are regular silicon diodes. And 1N4000 ones are the most common ones you'd find any AC to DC rectifier circuit. Okay. The series goes all the way from 4001 to 4007. The difference is that as the number increases, the reverse voltage handling capability increases. So 1N4001 can handle up to 50 volts in reverse bias. 4007 can handle up to 400 volts in reverse bias. You could potentially stick this diode into the wall outlets and it'd be fine. You could use it as a AC to DC rectifier. But obviously we don't want to do that. Not directly. So these diodes can handle a large amounts of voltage in reverse bias. Now, if you're looking at a diode that could break down at, let's say, 10 volts or 15 volts or 20 volts, right? So the mechanism that causes this to happen is known as avalanche. And what happens is, due to the specific amount of doping, you have certain charge carriers present. When you apply reverse bias, what you're doing is you're expanding the junction barrier, right? The depletion region. But at the same time, the electric field is increasing. And when the electric field is increasing, now you're supplying more energy to the semiconductor material. In other terms, you're supplying more energy to the electrons that are present in the semiconductor material. And at a certain point, the electrons acquire enough energy that that electric field will rip the electrons out of the lattice structure and create free electrons. In intrinsic material, the electrons hop free or are removed from the lattice structure due to thermal energy that is acquired. In reverse bias, the electric field is supplying that energy. Electrons acquire that energy and are now popped free. These electrons are now accelerated across the junction. So you have holes and electrons being created on either side of the junction. They are now accelerated across the junction. So you have current flowing in the opposite direction. And because of the high value of this electric field, the electrons acquire more energy and they're moving in a haphazard direction, haphazard manner, random movements. And as they're moving, they'll collide with other atoms in the silicon structure, in the semiconductor structure. When they collide with the other atoms, more electrons are now freed up. Those electrons are again subject to that electric field and now accelerated through the junction. They in turn will collide with other atoms, causing more electrons to be generated, which will go further down the chain. It's a cascading effect. It's a cascading effect that must be kind of controlled and stopped at a certain point. So this cascading effect creates an avalanche of carriers to be generated, hence the name avalanche. The collision process is known as the impact ionization process, because more charge carriers are created with impact, with collisions. And as they collide with other atoms, those atoms are ionized because the electrons are popping free. So that is known as the avalanche effect. And the avalanche effect occurs due to impact ionization. And as I stated earlier, no matter what effect is used to create the Zener diode, they are all referred to as Zener diodes. Okay. If we apply a large, if the voltage across these diodes keep on increasing with no control, eventually it's going to burn itself out. Okay, because it cannot sustain, that. Will the atoms move out of the structure? The answer is no. Well, I mean, if you supply sufficiently high enough energy, probably they could leave the structure. So they could have on. So the question being asked is, if they are heavily doped, wouldn't they have lower on voltages on the other side? Quite possibly, yes. Also depends on the material that we use. Okay, so let's look at the diode symbols. Diode symbols that we see here, normal diode right here, regular diode symbol. The whiskers on this diode right here, note that it's a Zener diode. This is regular diode. This is a Zener diode. And if the whiskers curve inwards, we get what is known as the Schottky diode. Schottky diode, named after the inventor Schottky. The special thing about this diode is that it's made up of one semiconductor material and one metallic material. So the junction is metal semiconductor. It's not semiconductor. It's metal semiconductor, so there's always plenty of free electrons available. Free charge carriers are always available. This results in a very low potential barrier. And so these diodes turn on at low voltages like 0.2, 0.25 volts. Hence, and also the speed of operation is fast. Okay, which is what we have been using in the lab. Fast switching, fast operation. Finally, I'd like to point out that if you're trying to model these diodes, okay, for a very accurate number for any kind of system, the more input we provide, the better would the answer would be, right? So in this model, we specify, in the SPICE model, we specify saturation, resistance, but these are the four main ones, right? Saturation current is part of the diode equation, so that's the most important. You have static resistance or series resistance, junction capacitance, these default values are automatically taken if the user does not specify them. So anytime you're performing a calculation, you always want as many precise numbers as possible, right? In order to get a more valid answer. And so the more quantities we can provide, the better the simulation results. And so that's what's being shown here. This last diode right here, where you see that capacitor at the end of the cathode, is a special type of diode known as a varactor diode, which is right here. But we are out of time, so if you have to leave, you can leave. I just have a couple more minutes and comments. I'll keep recording. So varactor diodes are basically diodes that have capacitance at the junction, and that capacitance can be controlled by the application of the diode voltage. So we can tune the capacitance by externally applied voltage. The capacitance arises because at the junction of the depletion region of the diode, we have charges that build up on opposite side of the junction barrier. Because opposite charges are being built up on the opposite side of the carrier, we can model it as a capacitance. Capacitance has the property of storing opposite charges on opposite sides of a barrier. And so the energy that is stored in that space charge region, the charges that are stored can be modeled accurately by modeling it as a capacitor. And so that is known as the junction capacitance, CJ. CJ. Okay, junction capacitance, CJ. The fixed junction capacitance is known as CJO. And at CJO, or CJ0, is a function, again, of the geometry and the doping profile of the diode. And then the applied voltage will change the space charge region, will expand or shrink it. And so the capacitance can be changed. And so that's the varactor diode. Okay. So we'll end class here today, and we'll pick up here again on Wednesday. We'll look at large models, large signal models of diodes and their applications.